Hello. Our project is detecting generative AI images versus original images using neural networks. Our teammates are myself Muralidhar Potugunta and my teammates are Venkatasai Vardhan Velivela and Kribakar Ravichandran. Let's get to the introduction. Today, we'll discuss the detection of generative AI images versus original photographs using neural networks. Generative AI models such as GAN, Stable Diffusion, and DALI have revolutionized how digital content is created. These systems generate highly realistic images which are indistinguishable from real world photographs. This innovation has opened doors for creativity in industries like advertising, art, and education. However, it also poses several critical challenges such as the spread of misinformation, ethical concerns, copyright violations, bias in data training sets, and potential societal and legal ramification. The need to distinguish between AI generated and authentic images is urgent given their misuse in fake news, malicious propaganda, and unauthorized reproductions. Our project addresses this need by leveraging the state of art neural network techniques to build a robust detection system capable of identifying AI generated content with accuracy. Now, let's get to the table of contents. Problem statement, objectives, data sets, network architecture, implementation, results, challenges and solution, conclusion, and references. Now, let's move on to the problem statement. Problem statement. The problem we tackle stems from the fundamental nature of generative AI. These models analyze vast data sets to generate content that mimics human created images. While this is a
చేసినాను
technical marvel, it comes with significant consequences. For example, AI generated images can be used to manipulate public opinion through fabricated news stories. The rise of synthetic media poses challenges in verifying content authenticity in journalism, digital forensics, and online platforms. Our system aims to address these challenges by using neural networks to analyze patterns, noise, and inconsistencies in image data to differentiate generative images from real world photographs. Let's move on to the objectives. To combat the challenges posed by generative AI, our project is guided by the following objectives: build a robust neural network, which is capable of identifying AI generated images with high accuracy, utilizing advanced pre processing techniques, which include resizing, normalization, and data augmentation to improve the model performance, ensure generalization across diverse datasets and generative models, making the system applicable to a wide range of use cases. Evaluating the real world applications, which include digital forensics, content verification, and combating online misinformation. Addressing key challenges such as dataset imbalance and adversarial robustness to create a reliable system. Let's move on to the datasets. Datasets. The effectiveness of any neural network depends on the quality and diversity of datasets used for training. For this project, we relied on publicly available datasets sourced from Kaggle and ImageNet for real-world photographs and Stable Diffusion and DALI for generative AI images. To prepare the datasets for training, the following pre-processing steps were applied. Resizing ensured all images had consistent dimensions suitable for input into neural network. Normalization adjusted pixel intensity values for uniformity across all images, improving model convergence during training. Augmentation introduced variations like rotation flips and scaling to enhance dataset diversity and reduce overfitting. These steps ensured that the model could learn effectively even when faced with challenges like data imbalance and varying image quality. Now, my uh, teammate would like to continue. Krupakar.
The model is a convolutional neural network model which is highly effective for image classification tasks due to its ability to extract spatial features from the images. Let's see the architecture in detail. Input layer. The input to the model is an RGB image of size 128 cross 128 cross 3. Resizing all images to this shape ensures uniformity. The first layer applies 32 filters of size 3 cross 3 with the ReLU function activation. This is followed by a max pooling layer that reduces the spatial dimensions, making the computation more efficient while retaining essential features. The same pattern is repeated with 64 filters in the second block and 128 filters in the third block, allowing the network to learn progressively more complex features such as edges, textures, and patterns. And then the flatten layer. After extracting features through the convolution and pooling, the output is flattened into a one-dimensional vector. Then the dense layer. A fully connected dense layer with 128 neurons and ReLU activation integrates all the features extracted from the convolution layers. To reduce the overfitting, a dropout layer is added. A dropout of rate 50% is applied, which is randomly disabling neurons during the training. Then the output layer. The final layer contains one neuron with the sigmoid activation function, which outputs a probability score. The score indicates whether the image belongs to Gen A or original class. Let's see why this design. This architectural design was carefully chosen to balance model complexity, performance, and generalizability. Let's break down the key reasons why this design was selected. Convolutional neural layers are the backbone of the model as they were well suited for processing image data. The layers learn spatial hierarchies starting from the low level features like edges and processing to high level features such as shapes and textures. By stacking convolution layers, the network builds a deeper understanding of the input layers. The first layer identifies general features like lines and curves, while the subsequent layers detect complex patterns, making it ideal for distinguishing between AI artifacts and real images. Increasing the number of filters in the deeper layers allows the network to capture a broader and more detailed range of features as the spatial resolution decreases. This ensures that the network focuses on meaningful patterns. So max pooling. Max pooling reduces the spatial dimension of the feature maps, lowering the computational loads and making the model more efficient. At the same time, it retains the most critical information by selecting the maximum value within a kernel. Then the pooling. The pooling after each convolution layer progressively condenses the learned features, making the network robust to small translations, rotations, and noises in the input images. Uh, After flattening the features extracted by the convolution layer, the dense layer acts as a classifier. The 128 neurons provided with sufficient capacity to learn the complex relationships between features without overloading the model with unnecessary complexity. Then the ReLU activation. The ReLU activation ensures non-linearity, enabling the network to learn intricate patterns in the data while avoiding the vanishing gradient problems common with other activation functions like sigmoid and tan. The dropout. The dropout with the rate of 0.5 is applied to reduce overfitting, especially since the dataset may include subtle differences between Gen AI and original images. By randomly disabling the neurons during the training, the model is forced to generalize better, ensuring it performs well on unseen data. The last layer activation is sigmoid. Why sigmoid? The output layer is a sigmoid activation function which is well suited for binary classification problems. It outputs a probability score of 0 and 1, where the value is closer to 1 indicate the original and value closer to 0 indicate Gen A. Varadan will continue the remaining.
The results of our project highlight the effectiveness of the proposed neural network in detecting AI generated images with remarkable accuracy. Our model achieved over 90% accuracy in detecting AI generated images versus real images, which is a significant milestone in this domain. This high accuracy demonstrates the model's ability to effectively extract and analyze pixel level features unique to each type of image. We validated our results using separate test datasets to ensure the robustness and the generalization of the model. A notable observation was that the model performed slightly better on AI generated images than real images. This could be due to the synthetic patterns in generative models being easier to learn than variations in real world photographs. Overall, these results highlight the effectiveness of our approach and underline the importance of balanced data and carefully pre-processed. One significant challenge was the imbalances in the dataset. For example, AI generated images, particularly those from the platforms like Stable Diffuse, were overtly represented in specific categories compared to the real world images. If left unaddressed, this imbalance could lead to the biased model training, where the model might lean to favor AI generated patterns while struggling with the real world diversities. To counter this, we manually reviewed and balanced the datasets by ensuring equal representation of categories such as landscapes, portraits, and abstract images. We also applied augmentation techniques like flipping, rotation, and color adjustments to increase the dataset variability. This helped improve the model's generalization across unseen data. Saying that, in conclusion, our project successfully developed a robust neural network capable of distinguishing AI generated images from real ones with a high degree of accuracy. This system addresses critical challenges posed by the generative AI, including misinformation, deepfake detection, and copyright concerns. Looking ahead, future work could involve enhancing the model to detect more sophisticated generative models methods or enabling real time detection for practical applications in fields like journalism or content verification. This project not only contributes to AI ethics but also serves as a foundation for further exploration in detecting and mitigating generative AI content risks. For doing this project, we came across these references. Our work was informed by foundational research. One key paper was detection of AI created images using pixel wise feature extraction. This paper explored techniques like photo response non uniformity and error level analysis. These inspired our feature extraction approach. Another important reference was deepfake detection, current challenges, and future trends, which provide insights into the advanced generative models and their detection strategies. It emphasizes the evolution nature of the challenges in this domain. We also referred to cutting edge work on convolutional neural networks, which are particularly well suited for detecting pixel level anomalies and patterns in images. These studies laid the groundwork for our methodology. And thank you for listening to the presentation.